Learning Goal 1.2 is about the mass spectrum and the average mass of isotopes of an element. So let's dive in. Remember that the mass spectrum was developed by a man named Francis Aston, who was a student of J.J. Thomson and worked with cathode ray tubes. What he discovered was that by bending the cathode ray tube and applying that magnetic field, he could separate out the atoms that had different masses from each other of a single element. We're talking about really small differences in mass, but he was able to do this first with neon and then with other elements as well. And this process has developed into even more detailed and intricate machinery, which now very accurately can count not only the mass of the substance, but also the relative abundance of that substance. So our modern mass spec data looks like a bar graph, which gives the mass along the x-axis, and then the height of the bar is the abundance of the number of those atoms that have that mass. So we can find the average mass of the substance by taking the average of all of these bars, right? So there's two kinds of ways that we could do that. One would be to multiply the mass by the height of the bar, and then add all of those together, mass times height, mass times height, mass times height, and then divide by the total number, or like all of the heights added up, right? So the total number of atoms. And that gives us the average mass per atom for that element. The other way to do it is to individually divide the height of the bar by the total height of all of the bars. So you're finding the mass percent, or the percentage of the atoms that have that mass, and multiplying it by the mass. So it's kind of like a distributive property problem. You can add it all up and then divide by like everything by the total, or you can take each peak, divide it by the total, multiply it by the mass, and add up all of those different parts. So you'll see sometimes this second method is easier if you're given percentages. If the bars are calibrated so that each bar is a percentage, then it's really easy to just change that percent to a decimal and multiply it by the mass and add it all up. If the bars are not calibrated, then the first method is usually the easier one. And you'll see that as we practice some of these problems. The other thing that you might need to find would be the relative mass, or the relative abundance of each mass. And that would not be from the mass spec, because you can do that relative abundance directly from the modern mass spectrometry data because of the height of the peaks. The instrument measures relative abundance. But in the methods of Aston, when he first had to calculate the relative abundance of each of his separated isotopes, he didn't have the calibration of the machine to that level of detail. So we do this by a system of equations, and this really only works if we have only two isotopes of an element, but you will possibly see this on the AP test. So we should go over it. So the way that this is done is by writing two equations. One equation is about the total number of atoms or molecules, and the second equation is about the total mass of those atoms or molecules. But we're going to mostly focus on atoms because we're focusing on individual elements and their isotopes. So we'll use neon for an example. And so when we talk about the relative abundance of each isotope of neon, what we know is the average mass of neon, which is 20.18. And we arbitrarily set the total number of atoms that we want to talk about at 100, because then when we finish this calculation, each of our calculated values will be the percent abundance part out of 100. So our first statement is going to be x plus y equals 100. That's x atoms of one isotope and y atoms of another isotope add up total 100 atoms altogether. Now we know the actual mass of each of those isotopes, we just don't know how much of each is in the sample. We know that one isotope of neon is neon with a mass of 20, and the other isotope of neon has a mass of 22. So we'll say that X has a mass of 20 and Y has a mass of 22. We also know the overall average mass is 20.18. So if we multiply X atoms times the mass of 20, we get the total mass of all of those X atoms. And if we multiply Y atoms by the 22, we get the total mass of all of those Y atoms. And then if we take the average mass and multiply it by 100, the number of atoms we have altogether, we should get the total mass of all of those 100 atoms on average. So that's what we do for our second equation. Again, the first equation is about the total number of atoms, and the second equation is about the total mass of those atoms. Now we have two equations and two variables, which we can solve by using any system of equations method. That could be graphing and finding the point where they overlap. That is probably not what you're going to do on the AP exam, because you can't use calculators on the multiple choice part, and graphing calculators you can use on the other part, but it's really simple to do this math just by using the calculation methods that we know for systems of equations. My personal favorite is the elimination method. We just take that first equation, multiply it by the smaller of the two masses. So in this case, 20. We multiply everything by 20 and then subtract that from the other equation. So this becomes 20x plus 20y equals 2,000. We subtract that from the other equation, and that eliminates our x values, and now we just have y. 22y minus 20y is 2y. 2018 minus 2000 is 18, so we have 2y equals 18, which means y equals 9% of our neon has a mass of 22, and that leaves 91% of neon having a mass of 20. So you can see this is a pretty simple method. X plus y equals 100, then the mass times x, the other mass times y, the average mass times 100. Multiply the first equation by the smaller of the two masses, subtract, solve for one of your variables, and then it's simple to solve for the other one because they have to add up to 100. All right, let's get this into your study guide, and then we'll practice some AP examples.
Here's your first AP example. This is a multiple choice question, so don't use a calculator and see if you can answer this question. Pause the video until you have your answer, and then when you're ready, push play to see if you got it right. All right, so this question is asking about element SB, which is antimony. So we need to find that on the periodic table and figure out that its average mass is 121.76. So looking at these graphs, we can eliminate A. It only has one isotope, which is exactly 122. We can eliminate D because this would have an average mass much closer to 124. Looking at C and B, we now can see that C has actually too much of the heavy isotopes, 123 and 124. So this average doesn't look like it would be closest to 121. So B is the best answer here. Here's your second example. Go ahead and pause the video. This one is a open-ended question, so you can use your calculator. When you're ready, push play to see if you got it correct. All right, so we're going to find the average atomic mass of livermorium. So we need to multiply each mass peak by its number of atoms or relative abundance. So we take each one of these peaks and multiply it by the height of the peak, which we can find on the y-axis. And we're going to add that all up. That will give us the total mass for all the atoms. And then we just need to take and divide that by the total number of atoms to find the average. When we do this on our calculator, we get 292.5 for the average mass of livermorium. All right, another multiple choice question. Please pause the video, try this one, and when you're ready, push play. Here we have another mass spec. So we're going to look at the possible atoms that and their atomic numbers that they could be. Aluminum is atomic number 13, magnesium is 12, iron is 26, and titanium is 22. And so we can eliminate C and D. If the total mass of the thing is 26, then we can't have iron or titanium because the atomic mass plus the neutrons should add up to 26. Also, the average mass here would be just a little bit more than 24, so we can find that on the periodic table as well. Aluminum is 26.9 and magnesium is 24.3. This looks like it's most likely magnesium. Choice B is the best answer. All right, that's it for this video. You're ready to move on to video number 3.